In this video, I want to explain something that is going to come up again and again over the next couple chapters. It's a very important concept, and this concept relates to actually how power plants work and how we get all the energy that supplies our houses, and our schools, and our streets, and your places of employment. So that's how important this concept is. And that concept is magnetic flux. Okay? So magnetic flux is really just the idea of how much magnetic field is penetrating a certain surface. Okay? So let's suppose that I have like a little square loop of wire, like this, right? So like a little square loop, right? And let's suppose that I have a magnetic field that is moving through it. Okay? So the flux is simply going to be, right, the magnetic flux, or in other words, how much magnetic field is penetrating this area, right? This has some area to it, right? Some length times a width, right? So magnetic flux is really just B times the area, right? How strong is the magnetic field times how big is the area that the magnetic field is actually moving through, all right? And flux is a very common concept that shows up in all of sciences, right? Like, let's say you have a fluid flowing through a pipe. That pipe has a flux, right? There's how much water is flowing through a certain area of a pipe, right? Like your veins, for example, there's a certain fluid flux that's happening through the surface area of your veins as it's traveling along through your body to give oxygen to all the parts that need oxygen, right? So in this case, to be a little bit more specific, and this won't always be the case, but this is a rectangle, right? So this flux will actually be B times length times width, right? But if it was a circle, right, let's say it was a circle instead, and you had magnetic field flowing through it, right, then it would be B times pi r squared, as you would guess. Okay? Now, what happens, though, if I actually tilt this, right? As you can see from this picture in the magnetic flux slide, if I tilt this a little bit, then the effective area, right? So let's say now instead it looks like this, right? But I still have magnetic field, penetrating it. But now you can see there's less effective area for the magnetic field to actually move through, right? So if I'm the magnetic field and I'm looking, I see, instead of this nice big surface, I see the surface kind of squished, right? And there's kind of less of it that I can actually go through. So as you move this area, right, the flux should be getting smaller and smaller and smaller, all right? So in other words, really, the true formula for flux is equal to B a cosine theta, because cosine theta is a function where if the angle starts out at 0, right, and that's, to be specific, that's the angle between the area vector. So the area vector actually points perpendicular out from the area, okay? So you can see here that the angle between the area vector and the B field is 0. Cosine of 0 is 1, and you just get BA, okay? But over here, right, if the area vector, so this is the area vector is now at some angle here, theta, then in that case, we will get a smaller cosine function, which reduces the flux a little bit, right? All the way to the point where if you have, this lying on this surface like this, then the B just slides right past it. It never actually penetrates the surface whatsoever, right? So in that case, you're going to have 90 degrees, right? Cosine of 90, we all know, is 0. So in that case, the flux would just be 0, right? So the flux can range from perfectly, the surface is perpendicular to the B field, but the area vector is parallel, and that makes it so that you have maximum BA, right? All the way down to it's totally flat, and the B cannot penetrate it whatsoever. All right? So that's basically the concept. That's magnetic flux. And it turns out that how much flux you have and the rate at which that flux is changing actually gives rise to an induced current inside that loop. But we'll talk more about that in the next set of videos. Okay, for now, I just want to just do one example so you're comfortable calculating this. It says what the flux, if you guys could go to that slide, please. It says this figure is a perspective view of a flat surface with area 3 centimeters squared and a uniform magnetic field. The magnetic flux through the surface is 0.9 Webers. So flux is measured in a unit called Webers, which is just WB. All right. Okay. Find the magnitude of the magnetic field and the direction of the area vector. Okay. So the actual picture gives you the direction of the area vector. We see here, according to this, that the area vector makes an angle of 60 degrees with the B field. Okay. So that makes our problem really easy. If we want to find the magnetic field, we have flux equals BA cosine of theta, right? We know the flux is 0.9 Webers, as the problem says. Okay. We want to find the B field. That's our unknown. I'm changing markers just because it's so squeaky and really annoying. Okay. So A is 3 centimeters squared. So I want to convert that to meters. 3, so that's 0.03 times 0.03, because it's squared. Sorry. Okay. 3 centimeters squared times. Okay. So in 1 meter is 100 centimeters. 1 meter again is 100 centimeters. So that gets us our centimeters squared. Okay. So 3 divided by 100, all right, is 0.03. Divided by another 100 is 0.0003. Cool. So then that area is going to be 0.0003 meters squared. And remember, our angle again is 60 degrees, so that's cosine 60. Okay? And yeah, for whatever reason, this final answer is not in my notes, which means that it's the universe telling us that the universe wants you to find the solution to this and put it right here and know how to solve for. Notice we didn't solve for flux in this. We used the flux to solve for what the B field must have been that's creating that flux. Okay? All right. This is just an introduction. You're going to end up seeing more flux than you care to see. You're probably going to say, what the flux, many times. Yeah, I just wanted to introduce that. We'll be coming back to it next chapter.